Okay, I want you to imagine, just for a second, an invisible, totally chaotic world right in front of you. A microscopic universe filled with literally billions of tiny particles, zipping around at blistering speeds, constantly smashing into each other and bouncing off the walls. I mean, it sounds like pure chaos, right? But what if I told you that out of this microscopic mayhem emerges perfectly predictable, measurable macroscopic rules? Well, welcome to This Explainer. Today we're taking a really fascinating journey from the micro to the macro, exploring exactly how these invisible collisions dictate the world around us. So here's our roadmap for today. We're going to hit the invisible world of particles, the rules of gases, speeding up chemical reactions, the art of chemical balance, and finally, Le Chatelier's shifting systems. Let's dive in.
Part 1. The Invisible World of Particles. Understanding KMT.
So KMT, that stands for the kinetic molecular theory, and it basically says that gas particles are in this state of constant random motion. Imagine a room literally full of hyperactive bouncy balls that just never, ever stop. There are no intermolecular forces pulling them together, they just fly right past each other. And when they do hit something, the collisions are perfectly elastic. That means absolutely zero energy is lost in the crash. In this weird little world, the temperature you feel is actually simply a measure of the average kinetic energy of all those bouncing particles.
So how exactly does this microscopic chaos build into something we can actually, feel? Well, it happens in 4 clear steps. When the temperature increases, we're basically adding kinetic energy. Step 2, the particles start moving faster. Step 3, because they're moving so fast, they collide way more frequently and with much greater force against the walls of whatever container they're in. And the final macro result in step 4, the pressure increases. So a simple microscopic speed boost creates a very real, very measurable physical push. The absolutely crucial point here is that this microscopic behavior scales up into unbreakable macroscopic rules.
Moving right along to Section 2, the rules of gases, macroscopic behaviors.
All right, so we've got the 3 heavy hitters of gas behavior to talk about. To really understand these laws, scientists essentially lock one variable in a room and see how the other 2 play together. For Boyle's law, temperature is the constant. For Charles's law, pressure is locked in. And for Gay-Lussac's law, volume is the constant. When we map these out, you can really see how temperature, pressure, and volume are engaged in this constant, delicate dance.
Now notice the difference in these relationships. Charles's and Gay-Lussac's laws show direct relationships, meaning if one variable goes up, the other goes up. They move together as a team. You actually experience Charles's law every single winter, when the cold temperature causes your car tires to lose volume and look a little flat. But then there's Boyle's law. It's kind of the odd one out because it's an inverse relationship. Think about squeezing a balloon. You're increasing the pressure on the outside, and as a result, the volume on the inside decreases. If you double the pressure, the volume is chopped exactly in half. They always move in opposite directions.
Wait, before we move on, I have to highlight a massive, totally non-negotiable mathematical rule here. When you're using literally any of these gas law formulas, your temperature must always be in Kelvin. Not Celsius, not Fahrenheit, Kelvin. You simply add 273 to your Celsius temperature. Why? Well, because the Kelvin scale has no negative numbers. If we use negative temperatures in our math, we'd calculate negative volumes and negative pressures, which physically makes absolutely no sense in our universe. Anyway, now that we know how gases behave, what happens when these moving particles don't just bounce, but collide with a purpose to create something completely new?
That brings us to Section 3, speeding up chemical reactions. Collision theory in action.
So collision theory tells us that a chemical reaction only happens when particles smash into each other with enough energy and the exact right orientation. So how do we hack the system to make reactions happen faster? We actually have 4 main tools in our toolkit. We can increase the temperature, giving them way more kinetic energy for harder collisions. We can increase the concentration, simply packing more particles into the space. We can increase the surface area, exposing more particles to the chaos. Or we can use a bit of a secret weapon, adding a catalyst.
But what's really fascinating about a catalyst is the actual why behind it. A catalyst doesn't just pump more energy into the system like a heater would. Instead, it provides an entirely different, much easier pathway for the reaction to take. It actively lowers the barrier to entry, the activation energy. It's like, instead of forcing particles to climb over a massive mountain to react, the catalyst basically blasts a quick tunnel straight through the middle of it. Pretty cool, right? But reactions don't just speed along infinitely. Eventually, things settle down.
Which brings us to Section 4, the art of chemical balance, dynamic equilibrium.
You can kind of think of a reaction like a busy two-way street. When it first starts, the forward rate of creating products is super high, and the reverse rate is literally zero because, well, there are no products yet to go backward. But over time, the forward rate slows down and the reverse rate speeds up. Eventually, they hit equilibrium. I want you to picture walking down an up escalator. If you walk down at the exact same speed the escalator is moving up, you look perfectly still to anyone watching. The action is happening, but the rates are completely equal.
Now, I need to point out a really common misconception here. At equilibrium, the rates of the forward and backward reactions are exactly equal. But the amounts, the concentrations of the reactants and products are just constant. They're steady, they're locked in, but they are not necessarily equal to each other. You might have 90% product and 10% reactant. As long as those percentages stop changing, boom, you have reached dynamic equilibrium. So we have a perfectly balanced system. But what happens when we intentionally mess with it?
And that takes us to our final section. Number 5, Le Chatelier's shifting systems, stress and response. This principle is basically nature's ultimate push and pull survival mechanism. Le Chatelier's principle states that if you apply a stress to a system at equilibrium, like if you poke it, heat it, or squeeze it, the system will shift its reaction to directly counteract whatever you just did. It constantly fights back to restore its balance. So this push and pull actually builds into some very predictable rules. If you crank up the temperature, the system basically says, whoa, too hot, and shifts toward the endothermic side to absorb that extra heat. If you decrease the pressure, giving the particles more room, the system shifts to the side that produces more moles of gas to fill up that empty space. It is just a constant, ongoing game of chemical tug-of-war. Let's actually bring this theory into reality with a pretty famous example, the production of ammonia. Think about the equation for a second. Nitrogen gas plus 3 hydrogen gases yield 2 ammonia gases plus heat. It's an exothermic reaction. And notice the moles here. On the reactant side, we have 4 moles of gas total. On the product side, we only have 2 moles. That difference in the space taken up is going to be incredibly important. Now let's play Le Chatelier's game for a second. What happens if we cool this system down? We're essentially stealing its heat. Well, the system hates that stress. So to counteract the loss, it shifts to the right, toward the exothermic side, to literally manufacture more heat and warm itself back up. And as a brilliant side effect, by shifting right, we naturally produce a massive amount of extra ammonia.
Right, so what about pressure? If we throw this reaction into a container and squeeze it tight, increasing the pressure, the system feels incredibly cramped. How does it relieve that stress? It shifts to the right again. Why? Because the right side only has 2 moles of gas compared to the 4 moles on the left. The system literally compacts itself into fewer molecules to take up less space and relieve the pressure. I mean, it's absolutely elegant.
So, from microscopic bouncy balls to the massive industrial production of chemicals, it is all governed by these beautiful, unbreakable rules of motion, collision, and balance. It kind of makes you wonder, doesn't it? If the very foundation of our universe is built on constant random motion and reacting to stress, are we all just shifting to find our own equilibrium? Think about that until next time. Thanks so much for joining me on